we were asked to figure out the potential energy change of a satellite between 7,000 kilometer and 12,000 kilometer distance from the center of the Earth. Now, gravitation is a conservative force, so the path doesn't matter. So we just consider a path that goes directly from a 7,000 meter position to a 12,000 meter position, moving straight away from the center of the Earth. That is, we use a radial path. Okay, so we get, naturally we partition etc., as we saw in the preceding class, and we end up with an integral of big G, big little m, big M over r squared from 7,000 kilometers to 12,000 kilometers. And that integral turns out to be big G, little m, big M over r evaluated between the 7,000 and 12,000 kilometer positions. Now, plugging in big G here, little m, and big M being the mass of the Earth, we are left with just the 1 over r, which we evaluate between the limits, and we get this. Okay, I don't have to read it to you. Now, it looks like this is going to come out positive, but be cautious, be cautioned, it doesn't, because 1 over 7,000 is bigger than 1 over 12,000. So you're subtracting the bigger from the smaller, and you're going to end up with a negative result. Now, I did some stuff here, and I'm not even sure my result is correct. You can check it out. 10,000 kilometers is 10 million meters. And actually, I did kind of screw that up. That should have been 10 to the negative 6th here. Since I kept the 12 and the 7, it's 12 times 1,000. Well, let's not worry about my shortcuts, because you can substitute this yourself and get your own result, and you'll see that when I had the 10 to the 9th joules here, I believe I was off by a factor of 10. Okay. So I'm thinking this is what you get, but I'm still not sure. I did some arithmetic. You know, I put this over common denominator of 84, and I got 5/84ths, negative 5/84ths, and I approximated that as about 0.06, and multiplied 0.06 by this and got this. Now, actually, I think that might have worked out, but you check it out. This is just details. The essential thing to see is this equality. Okay? And that's not hard to see. Also, you know, understand that you got to articulate the units. You don't come out with Newton meters squared here or Newton meters here if you don't do something about that kilometer. And you know what to do, so I'm not going to discuss that. Okay, now, when I ask what the change in the kinetic energy is here, nobody could tell me what the work energy theorem was, which I found a little shocking, because you're about to be tested over energy, among other things, and it includes the work energy theorem, potential kinetic energy, and all that stuff. And you have to be able to derive the fact, at least for a constant force acting on a constant mass, that the change in kinetic energy is equal to the work done by the net force on that mass. So, the work done on the system, well, what work is done on the system here? Well, this is the work done by gravity on the system being now the satellite. The work done on the satellite by gravity is negative 1.2 times 10 to the 10th joules. Okay? That is, if this is the net force, then this is the change in kinetic energy. And it's going to turn out that it's actually so. But we want to interpret this in terms of potential and kinetic energy. So, knowing that the work done by the net force on the system is the work done on the system by conservative forces plus the work done by all your non-conservative forces, net conservative, net non-conservative, because forces are one or the other. Now actually, you know, rubber band exerts both kinds of forces. We can think of it that way, but we separate each force into a conservative and a non-conservative component, and some forces are just conservative, some forces are just non-conservative. As you are seeing in multivariable calculus at this very moment, the gravitational force is conservative. We can express it as the derivative of the gradient of a potential function. It's path independent. Okay, the gravitational field is a path independent field. For all those reasons, the gravitational force comes under this heading. Okay, now, what do we call the work done by conservative forces on a system? What does that bring you in mind of? Another definition that I told you 3 months ago that you need to carry with you for the rest of your life, and nobody could even begin to quote it, that the change in potential energy is equal and opposite to the work done by conservative forces. So this is equal and opposite to your potential energy change. And then over here you have your work done on the system by non-conservative forces. For an orbiting object, there's very little stuff out there to slow it down. So the only force that exerts a significant, that does significant work on a satellite, an ideal satellite, is the gravitational force. Now every satellite carries a little bit of booster fuel because it does run into a small amount of mass as it goes through its orbit and loses a small amount of kinetic energy with every orbit, of total energy with every orbit. It loses energy to non-conservative forces. That's a very small amount of energy compared to the total energy of the satellite. So this is a small amount, and we're going to ignore it now and say it's negligible, at least for one orbit. That's pretty much the case, as long as you're not in a very low Earth orbit. Okay, so for a satellite, this is 0. So I'll just say, okay, that's 0, that's 0. I stated here the work done by non-conservative forces is 0 or negligible, and that means we're going to let it be 0 even if it really isn't. So the change in potential energy, well, change in kinetic energy is equal and opposite to the change in potential energy, and this is what you need to think in terms of, and this is what you need to understand. Now we have the intuition that when something moves away from the Earth tries to pull it back, so to move it away we got to do work on it so the potential energy increases. That's perfectly correct. But in terms of our definition of potential energy, it's going to be equal and opposite to the work done by the gravitational force on the object. If we're moving away from the Earth, gravitational force pulls in the opposite direction, so the work done by the gravitational force is negative. So as we move away, the change in potential energy is positive. We've got the integral here. The integral gives the work done on the satellite by the gravity is negative 1.2 times 10 to the 10th joules. Change in potential energy is the negative of that, or positive 1.2 times 10 to the 10th joules. So the kinetic energy change is going to be equal and opposite to the change in potential energy, meaning since the potential energy goes up, the kinetic energy goes down. As we move away from the Earth, we expend kinetic energy to increase our potential energy. As we get out to the far point of the orbit, we start coming back toward the Earth, and potential energy decreases, kinetic energy increases. So when you get back to the closest point, kinetic energy is at its maximum, and now we start moving further away, we lose potential, and the cycle continues. Okay, so in any case, change of kinetic energy, and I change the 10 to the 9th to 10 to the 10th because I think that's right. Okay. Now we can also see what the kinetic energy at, let's say, 7,000, I'd say 10,000 meters per second. If we square 10,000, we get 10 million. So actually I think we probably got a lot more kinetic energy than I'm giving us credit for in potential energy change. Well, check my figures here. I don't trust these figures. I made a mistake already. And I'm not reconciling this with the kinetic energy of a 500 kilogram satellite at the speeds we're talking about. Oh, wait a minute, that's, never mind, it's 100 million, so that gets us up into the, still not quite, now I'm not coming up with quite enough kinetic energy. You work it out. Okay, now, we want to know what the total energy of the satellite is relative to the surface of the Earth. Okay, well, total energy relative to the surface of the Earth is the sum of its potential and kinetic energies. The potential energy relative to the surface of the Earth at the 7,000 kilometer position is this integral. From surface of the Earth up to 7,000 kilometers, we evaluate that integral the same as we did this one. And potential energy is actually the negative of this integral, because this integral comes out negative, the potential energy is going to be positive for the reasons we discussed over here. So I was missing a negative sign when I wrote this down. We want the kinetic energy in a circular orbit at 7,000 kilometers. Okay, so how do we get the kinetic energy? Well, if we've got the mass of the satellite, we calculate the kinetic energy by first finding the velocity. How do we find the velocity? Well, the velocity of a circular orbit is governed by the fact that the centripetal force is equal to the gravitational force. Centripetal force is mv squared, gravitational force is what we have here, big G, little m, big M over r squared. And we can solve that for v. We get v is the square root of big G, big M over r. V squared is this without the square root, and our 1/2 mv squared is then 1/2 m times the big G, big M over little r. So we have our expression for the kinetic energy. And we can evaluate that for the given mass of the Earth and the given 7,000 kilometer radius, and we'll get a kinetic energy. We add that to our potential energy. That's the total energy we have in that orbit relative to the surface of the Earth. That's how much energy we got to put into that 500 kilogram satellite using our rocket. Now we need a lot more energy than that. The fuel has to carry much more energy than that because the fuel has to raise itself and the rocket as well as the payload. So you got to have a tremendous amount of energy in the rocket fuel. That's a different subject, okay? So the idea of potential plus kinetic energy relative to the surface of the Earth, that's very relevant in rocket science.